Okay guys, so here's an induction question. I'll do 3 of them for you. So this is induction to prove a series. So this series is 2 plus 4 plus 6 plus 8 all the way up to whatever number can be, I suppose, found by going n multiplied by n plus 1. So what we mean there is, let's say I want to find the first two terms added together. Well, then I put in 2 here. Okay, so let's see if that works. So the first two terms added together would be 2 plus 4. And that equals, well, first two terms added together, so it's the second term. So we put in 2 for n. That's 1. So that would be 6. And let's see if it works. 2 plus 1 is 3, multiplied by 2 is 6. So there we go. So we're after proving it works for the first two terms anyway. If I wanted to find out what 2 plus 4 plus 6 plus 8 is, I'd put in 4 here. Why 4? Because we're going all the way up to the fourth term. Look, 1, 2, 3, 4. Okay. If I wanted to find out what the first 100 terms added together would be, I'd put in 100 here. And I could check if it works by just adding 2, 4, 6, 8 all the way up to the first 100. But that doesn't prove that it works for every single number right up to infinity. Because whatever number I put in here, I can always say, well, does it work for the next number? So the only way of proving that the sum of however many numbers up all along is given by putting in the term here, the term there, and multiplying it out, we're going to have to use induction. Okay, so here's how we do it, right? And we know this already, so step 1. Step 1 is prove for n equals 1. So basically prove for n equals 1 means prove for the first term. So the first term is 2. Okay? Let's see if I put the first term, so 1 in here, stands for the first term. Let's see if I put 1 in for n, will I get 2? So 1 plus 1 is 2, and multiplied by 1 is 2. So yes, works for the first term. Next step, 2, assume for n equals k. So assume that's true when I replace n with k. Okay, so what I mean by that, 2 plus 4 plus 6 plus 8, if I go all the way up to k, so a certain number, well, that should be the same as k plus 1. So I'm just after substituting the n's with the k's. Okay, so I'm going to assume that's correct. I don't know what's true, but I'm going to assume it's true. And then step 3. I'm going to prove, or try and prove anyway, prove it's true for n equals k plus 1. So what I mean by that, put in brackets, what I mean by that is I'm going to assume that this works all the way up to a number. And now I'm going to assume it works for the next number, so k plus 1. Plus 1 will be the next term. Okay? So here we go. 2 plus 4 plus 6 plus 8 all the way up to 2k. So that's all the way up to a certain number plus the next number. Okay, and the next number is 2k plus 1. And I'll put it in brackets. Okay? So I'm going to assume it's correct for this number all the way up to here, and then I'm going to prove that it's true for all the way up to this and the next number. Okay? And that would be equal to, anywhere I see k, or here, sorry, n here, I'll put in k plus 1. So we have k plus 1 replaces that in. Another bracket, k plus 1 will replace that in, and we have a plus 1, so I'm going to just put it all in brackets. Okay, so I just put the brackets there to neaten it up a bit. Now, if I can prove that all of this is the same as all of this, then I'm after proving that this here equals all of this, no matter what number I put in for n. Okay, so I'm going to look back at this assumption I've made, and I've assumed that all of this is the same as this. Well, look at this. 2 plus 4 plus 6 plus 8 all the way up to 2k. Well, I can replace that with that, okay, because they're saying they're equal to each other. Okay, so instead of writing this, I'm going to write k plus 1. But I can't forget about this, so I have to still put this in. It's 2k plus 1. And over here, I'm just going to neaten this up a bit, so it's k plus 1, and then we've k plus 1 plus 1, which will be k plus 2. Okay, so if I can multiply this out now, Holly made a great observation it was earlier today, and she said, well, actually this is the same as this. I'll just do it out here, because she said if I'm multiplying these two things together, how I multiply it is I go k plus 1 and then plus 2 k plus 1. Like, that's how I would multiply out this. And if you look here, it's actually the exact same. Okay, so that there is a proof there already. But I'm just going to multiply the both out, and we'll prove that they're the same. So k by k is k squared, k by 1 is k, plus 2 by k is 2k, plus 2 by 1 is 2. And over this side, multiply these two out, so it's k by k is k squared, and k by 2 is 2k, and 1 by k is 1k, and 1 by 1 is 2. And we just simplify it, so we have k squared plus 3k plus 2 on this side, and over here we have k squared plus 3k plus 2. So they're the same. So we're after proving that this here, no matter how far it goes up, we can actually find the same over here by putting in whatever term we want. Okay. And just to finish off then, I'll say therefore, because I want to answer what I'm asked, so therefore 2 plus 4 plus 6 plus 8 all the way up to 2n does equal n plus n plus 1. Okay, so that does equal it. Okay. Okay, so next one, question 2. We're asked to prove again that this series here, so 1 plus 4 plus 7 plus 10, all the way up to 3n minus 2, okay, so all up to a whatever number, as far as it goes, can be represented by n over 2 multiplied by 3n minus 1. So what they mean is, if I want to find the third term, so look, here's the first term, second term, third term. If I want to find the third term, if I put in 3 in for n, it should spit me out. What is it? 1 plus 4 plus 7, which is 12. Okay, so it should do that for me. If I want to find the fourth term, which is up here, the sum of the first 4 terms, I'll put in 4 here, multiply it out, and it should give me what these 4 are, the sum of those 4 terms. And that should work all the way up to infinity, okay, all the way up to every single number. The problem is I can't prove that, because no matter what number I pick to put in here, someone else can come along and say, ah yeah, but does it work for the next number? So proving this with numbers doesn't actually work, okay, because there's an infinite amount of numbers. So we have to do it by induction, just like we've been doing already. So step 1, prove for n equals equals 1. So basically proof for the first term. Okay, so the first term here is 1, and if I put in, and also 1 is the first term, so if I put in 1 over here, it should spit me back out 1. So let's see. Okay, so lose my train of thought now. No, sorry. So okay, so we have 1 here equals a half. Now 3 ones are 3. Okay, sorry, that should be a 1. Sorry now. Yeah. Okay, so 3 ones are 3 minus 1. So 1 equals a half. 3 minus 1 is 2. And a half of 2 is 1. So yeah, it works. Okay, it works for the first term. So when I put the first term in there, it does spit me out 1. It probably works for the second term as well. If I put 2 in there, it probably would spit me out 4 plus 1, 5. And if I put 3 in there, it should spit me out 7 plus 4 plus 1, which is 12. Okay, so it should do that. Okay. But as I said, we can't try every number. Okay? So, step 2. Okay, we're going to assume true for n equals k. So we're going to assume it's true for a certain number. We do that by getting 1 plus 4 plus 7 plus 10 plus all the way up to 3k minus 2 should be the same as k over 2 3k minus 1. Okay, so we're going to assume that, and then we're going to prove that it's true for the next number, so k plus 1. So step 3, prove true for n equals k plus 1. Okay, so again, 1 plus 4 plus 7 plus 10 plus all the way up to 3k minus 2 to plus 3k plus 1 minus 2. Okay, and again I'm just drawing it out in brackets. So again, anywhere I see the k, I put in the k plus 1. Okay, so this goes all the way up to a number, and then the next number, k plus 1. And I want to prove that that's correct for k plus 1 over 2, 3k plus 1 minus 1. So again, over here, anytime I see the k, I put in the k plus 1. Okay, so now I need to just show that all of this side equals this side. Okay, well, the first thing I'll do is take the first piece of it, and I'll say, well, this all equals this. Okay, so I'll rewrite this as k over 2, sorry, 3k minus 1, and then I will add this to it, which is 3k plus 1 minus 2. Okay, and trouble brackets. Okay, and hopefully I can get that to equal k plus 1 over 2 all multiplied by 3 k plus 1 minus 1. Right, so we have to use a bit of algebra to tidy this up. Okay, well, the first thing I'm going to do is I'm going to tidy this up because it's a bit of a mess. 3k minus 1 equals, we have 3 by k and 3 by 1, so it's 3k and 3 by 1 is 3, and then minus 2, which is plus 1, and that's not an equals, that's a plus. Okay, and if I can tidy up this side, well, actually, remember that trick I used, I often use, if we have a fraction multiplied by a number over here, I can just put it all over. the denominator. Okay, so we've k plus 1 on top, multiplied by, and I'm going to simplify this out, so 3k is 3k, and 3 ones are 3, minus 1 is plus 2. Okay, so I suppose I can put this over 2 then, so I go k 3k minus 1 all over 2, but I'd like to have this all over 2 as well, so I'll do that. So if I divide this by 2, I'll have the 2 under it all, but I can't just divide this by 2, I'm going to have to multiply it by 2 as well, so here we go, I'll multiply by twice 3k plus 1. Okay, so see what I'm after doing there. It was just 3k plus 1, but now I've put it over 2, but now I've multiplied it by 2 again. And it just allows me to get it all over 2. That will equal k plus 1, 3k plus 2, all over 2. Okay. Right, let's start multiplying it out then. K by 3k, 3k squared, minus k plus 6k plus 2 all over 2 equals, well, k by 3k, 3k squared plus 2k is k by the 2, and then 1 by the 3k is plus 3k, sorry, and then 1 by 2 is 2, and that's all over 2. Okay, right, nearly there. Just to tidy it up then, we have our 3k minus k plus 6k is plus 5k plus 2 all over 2 equals, and then 3k squared again, 2k plus 3k is plus 5k plus 2 all over 2. So they do equal each other. So if they do equal each other, we'll say therefore, and our original thing we had to prove all the way up to any given number can be got by using this formula. Okay, so we've proven that it's true.